Hi everyone. In the last lecture, we have seen the introduction of register and counter. So what is a register? Register is basically a collection of n flip-flops. So this is an n-bit storage device. Okay. And you know one flip-flop can store one bit. So if you want to store n bits, if you want to store, for example, 4 bit, then you need 4 bit, then you need 4 flip-flop. Okay. So basically register is an n-bit storage device. Now, let us see. So for example, this is your flip-flop. Okay. Now one flip-flop can store 1 bit. So this flip-flop can store 1 bit. If you want to store 4 bit, then what you need? You need 4 flip-flop. So this is a 4-bit register. If you want to store 8 bit, then you need 8 flip-flop. So this is a 8-bit register. So basically this is how you can, okay. So register, what is the register? A register is very simple, that this is a n-bit storage device. So to store n bits, then what you need? You need n flip-flop. Okay. So I can say that register is basically n bit structure consisting of flip-flops. So this is a collection of n flip-flops. Okay. Now let us see the next. So now let's create our first type. Okay, first register we will create. So remember, this is okay. Let's create very simple, very simple type of register we will create. So let us assume that you want to create this type of register. Okay, so let's see this type 1 register, very simple type of register we will study. So let us assume you want to create a 4-bit register. Okay, so this is what you want to create. You want to create a 4-bit register. Let's call it register R. Okay, and this you want to create a 4-bit register. So what we need? We need 4 flip-flop. This is what you need. So okay, so this is our objective. What is our objective? Our objective is to create a 4-bit register. Now this is a 4-bit register. In every flip-flop you can store 1 bit. Okay, now let us assume that you want that, okay, what you, for example, you want to store the data 1001. Okay, this is what you want to store. Then what you can do? Okay, let us assume that to store this data, what you want to do, this is your objective, that okay, insert this data like this. Okay, 1001. Okay, so this data 1 should be stored in this flip-flop, and this data 0 should be stored in this flip-flop. Okay, so this is what you want. And you also want, let us assume that once this data is stored, now this data that you are applying, once this data is stored, now what you want, you also want to read this data from this register. So this type of register you want, in which you can store the data in parallel. So this data you want to store in parallel. Okay, so this data should be stored in parallel, and also you want to read this data in parallel. Okay, so this type of register you want, this is your objective. Okay, so remember, I am just telling you that this type of register, let us assume you want to create this type of register. In this register, basically this is a 4-bit register in which the data can be stored in parallel. Okay, so this data we are storing in parallel, and this data we are also accessing, we are also reading this data in a parallel. Okay, so this type of functionality you want. So this is your objective. Now let us see how to create this type of register. How can we create? Okay, so you can notice the first thing is you want 4-bit register. So what you need? You need 4 flip-flop. Okay, so very simple, that you need 4 flip-flop. Now these flip-flops can be any flip-flop. For example, they can be D flip-flop, JK flip-flop, okay, SR flip-flop, they can be anything. Okay, now for simplicity, okay, we will take D flip-flop. Actually, usually, okay, what happens that in registers we normally use D flip-flop, because you can notice this D flip-flop. D flip-flop, okay, the name itself is telling you this is data flip-flop. This D flip-flop is actually the main functionality, okay, of D flip-flop is basically data storage. So that is the reason this is also called data flip-flop. Okay, this is also called a delay flip-flop. We will see what is, okay, so you can notice this D flip-flop, the main, why this D flip-flop is popular, because in this D flip-flop what you can do, this is your D flip-flop. In this D flip-flop you can notice, let us assume this D flip-flop is positive as triggered. So this is your clock. Okay, and this D flip-flop is positive as triggered. Now in this D flip-flop you can notice that whatever data you want to store, just put that data. Okay, for example, if you want to store data 0, then all you have to do, just put this data. Now what will happen, whenever this, okay, whenever this clock will go from low to high, means, okay, whenever this positive edge will come, okay, whenever this rising edge will come, then what will happen, this data will be stored in this flip-flop. What it means? Data is stored in this flip-flop. What it means? It means this data is available on this output. Okay, so now this data is available on this output. So you can notice in this D flip-flop, whatever I want to store, okay, this is your D flip-flop, whatever I want to store, just put it. Okay, and then what will happen when, okay, so this is your, let us assume this is your clock, and this D flip flop is positive as, let us assume this D flip flop is positive as triggered. Now what will happen whenever this rising edge will come, okay, whenever this clock will go from low to high, then what will happen, this data will be stored. Okay, so this data will be stored. What it means, data is stored in a flip flop. What it means, it means that it is available on the output. Okay, so that is the reason I told you that in registers usually, okay, normally, okay, we use D flip flop. Okay, so now, so let us assume that you, okay, so this is our objective. We want to create this type of register in which we have 4 bits. Okay, we, in which we can store 4 bits, and we can store the data in parallel, and we can read the data in parallel. Okay, so this type of functionality we want. Okay, now how to create? So we have 4 flip flops. So this is a D flip flop, and this is a D flip flop, and this is a D flip flop, and this is also a D flip flop. Okay, now, and I told you that in the registers, all these all these flip flops, they basically have a common clock. Okay, so they all have a common clock. Okay, so you can notice they all of them have a common clock. This is the common clock for all of them. Okay, now, okay, so this we have already seen that in a register, if you have n flip-flop, basically if your register is n bit register, then it means you have n flip-flop. Then these flip-flop, they have a common clock. Okay, so you can notice that these flip-flops have common clock. Okay, now, so this one objective is over. So we want to store 4-bit data, that is fine. But now we want to store them in parallel. Okay, so what we want to do, we want to store this data in parallel. Okay, so what I can say that like this. Okay, so the data I want to store in parallel. Okay, so I can say that if this is your data, let us assume you want to store this data you want to store 1000, this data you want to store. Then what you can do, very simple, you apply this data, okay, on these flip-flops in parallel, you apply. Okay, now, so this parallel, this is called paralleling, means I want to store the data in parallel. Okay, so okay, I also want to receive the data in parallel, I also want to read this data in parallel. Then what I can do, this is what I can do. Okay, so I can basically read this data here. Okay, I can read this data, I can read this data, and I can read this data. Okay, so you can notice that this is how we can do. Okay, so you can store the data in parallel. Okay, you can read the data in parallel, and you can store 4-bit data. So this functionality we want. Okay, we wanted to create this type of register. So this type of register we can very easily create. Okay, so this is how we can create this register. Now you can notice that in this register, what will happen now, because you can notice all these flip-flop, they are controlled by the same clock. Okay, so now this clock is all these flip-flop, let us assume these flip-flop are positive as triggered. So you can notice this flip-flop, this and this and this, all these are basically positive as triggered flip-flop. Now what will happen, this is going to happen. So okay, what you are doing, you are applying these inputs. Okay, so this data you are applying, okay, in parallel. Now what will happen, when this clock will go from low to high. Okay, this is your clock, and when this clock is going from low to high, then what will happen, then this data will be stored, because you can notice this, all these D flip flop, these are positive as triggered flip flop. So what it means, it means that whenever this clock goes from low to high, then this input data will be available on the output. So now what will happen, when this clock goes from 0 to 1, when this clock goes from low to high, then this data, input data, will be available on the output. Okay, so I can say that this data will be available on the output. So this is how basically you can store the data. Okay, if you want to store this data in parallel, you can just put this data in parallel, and then whenever this clock will go from low to high, then this data will be stored in these flip-flops. Remember, storing the data in a flip-flop, what it means, it means that data is available on the output. So okay, so let me just write this here, that what I mean by, okay, when we say that storing data in a flip-flop, what it actually means, it actually means that that data is available on output. It means that that data is available on output, on flip-flop output. Okay, so this is the point. And similarly also, let me tell you that flip-flop output is called flip-flop, this is flip-flop output, this is called state of flip-flop. Okay, so this is called state of flip-flop, because flip-flop output means the data which is stored. Okay, so if flip-flop output is 1, then it means that 1 is stored. If flip-flop output is 0, then it means 0 is stored. So flip-flop output means basically the data which is stored. Okay, the data which is stored, which is stored. Because I told you that storing the data in a flip-flop, what it means that data is available on the flip-flop output. So flip-flop output means the data which is stored, and the data which is stored, that is basically the state of flip-flop. Okay. Okay, so this is how you can create. Okay, so this is our objective. We want this type of register. This type of register, we call it parallel in, parallel out register. Okay, because you can notice the data, we are storing the data in parallel and we are reading the data in parallel. So this type of register is called parallel in, parallel out. Okay, so you can notice this is how we can implement this register. Okay, so this type of register you can very easily implement like this. Okay, so this is the point you can notice. So this type of register, so basically we have implemented parallel in, parallel out register. Okay, in a parallel in, parallel out register, we can store the data in parallel, we can read the data in parallel. Okay, and you can notice because we have 4 flip-flops, so we can store 4 bit of data. So this is a 4-bit register, so I can say this is a 4-bit parallel in, parallel out register. Okay, so this is our first register. Now you can notice that okay, so this is the logic. You can just read this. These slides I have taken from NPTEL. Okay, you can just see. Okay, now this parallel in, parallel out register. Okay, this is the symbolic notation for this, because okay, this is the implementation. You can notice this is the actual implementation. Okay, but the symbolic notation is this. Okay, what we can say, that this is your, okay, this is your 4-bit parallel in, parallel out register. This is your parallel in, parallel out register, in which the data is stored in parallel. Okay, so we put like this. Okay, and the data can be read in parallel. The data we can read in parallel. Okay. Okay, and there is a common clock. There is a common clock in all the flip-flop. In the here you have 4 flip-flop, so they are basically operated by the common clock. Okay, and remember what this symbol means. Let me tell you what this actually means. This actually means that there are 4 lines. Okay, and this also actually means, this also means that there are 4 lines. So okay, so remember this arrow. Okay, this is called vector notation. Let me tell you, this is called vector notation. What is vector notation? So vector notation is like this. Whenever we put like this, okay, then it simply, okay, for example, let us assume I put like this, then it simply means that I have basically 3 lines. Okay, so this is the vector notation. So you can notice this is the actual implementation of parallel in, parallel out register, and this is the symbolic notation. Okay, so we have basically 4D flip-flop we have. Okay, so 4 inputs, these are the parallel inputs and these are the parallel outputs. Okay, this is the common clock. Okay, and you can notice we can also have clear input. If you want to clear the register, if you at any point of time, if you want to clear the register, then what you can do, this is your clear input. Okay, and you can notice this means that this is a low, or you can notice this is active low. Okay, this means active low clear input. What it means, that when clear is 0, okay, when clear is 0, then what will happen, this this data, this register will be cleared. Okay, so cleared means this register basically will have the 0 0 0 0. Okay, so this is the point. Okay, so now you can notice we have seen one type of register, parallel in, parallel output register we have seen. Okay, so you can notice the register is basically, okay, in register there are two main applications of register. Let me tell you, one is data storage. You can store the data. Okay, and also there is something called data movement. Okay, and how the data is moving, how the data is moving from one register to another, or within a register. Okay, how the data is moving. Okay, so these are the basically two main functions of a register we will see. Okay, now let us see. Okay, if you want to understand register, then you need to understand three things. These are the three things you need to understand. One is you need to understand flip-flop. Okay, okay, and also you need to understand the storage capacity of register, and also you need to understand how the, okay, data is moved in a register. Okay, let's see one by one. So you can notice, okay, how a flip-flop stores the data, this you already know. Okay, this we have already seen, that a flip-flop can store data. Okay, so this we have already seen, one flip-flop can store 1 bit of data. Okay, or also how flip-flop stores the data, this we have already seen, that this is your D flip-flop. Whenever this clock is going from low to high, okay, let us assume this D flip-flop is positive as triggered. What it means, it means that whenever this clock is going from low to high, then this input data will be available on the output. Okay, so this we have already seen, how a flip-flop stores the data bit. So this we already know. And the second is the storage capacity of a shift register. Okay, so what is that? Storage capacity of a shift of a register, basically I can say the storage capacity of a register. Okay, so what is the storage? What do we mean by storage capacity of register? So this we have already seen. If you want n bit register, then you need n flip flop. Okay, if you want 4-bit register, then you need 4 flip flop. You need to connect a 4 flip flop because one flip flop can store 1 bit. Okay, and the next point is how to move the data. Okay, what that means? That means that within a register how the data is moving. Okay, or also between two registers how the data is moving. Basically we need to see, okay, that how the data is moving between the flip-flops of a register. So you let us assume this is your register. In this register you have, let's assume 4 flip-flops. Now we need to understand how the data is moving within these, okay, between these flip-flops. Also we need to understand how the data is moving from one register to another. Okay, so this is called data movement. Okay, so I told you that register has two applications. One is data storage and another is data movement. Okay, so you can store the data, that is fine, but now you can also move the data. You can move the data from one register to another. Okay, this you have seen many times. For example, let us assume this is your register RA, this is your register RB. Okay, and let us assume this is your data, and now this data you want to copy in this register. Let us assume this data you want to copy in this register. So this data you want to copy here. This is called data movement. Okay, so this is called, basically this is from one register to another how data is moving. Also we need to see how the data is moving between these flip-flops within this register, how the data is moving. Okay, whether this data is going from left to right, or whether this data is going from right to left, or whether this data is basically, okay, going, you can notice, in parallel. Okay, so all these things we have to study. Okay, now you can notice, depending on how the data is moving, okay, depending on the data movement, okay, you have many different type of registers. Okay, so you can notice based on data movement, how the data is moving, you have many different type of registers. For example, let us assume you have a register in which the data can move, okay, only in a serial manner. Okay, only in a serial manner. Then this is called serial in serial out register. Okay, and all these registers we will study in detail, but you can notice that in this register, just focus on this register. In this register you can notice that the data is going from left to right. Okay, and this data is going in a serial manner. Okay, so one bit, okay, one after another. So this data is basically, this type of register is called serial in serial out register. Okay, and you can notice the data is going from left to right, so this is called shift right register. Okay, now focus on this register. In this register the data is going, okay, in a serial manner, but this data is going in the left direction. So I can say that this is a shift left register. Okay, and you can notice this register we have already seen. The data is also, we are storing the data in parallel and we are reading the data in parallel. So this type of register we have already seen. This is your parallel in parallel output register. Okay, another type of register is this, where the data is stored in parallel, but it is read, okay, we read this data in a serial manner. Okay, so data is stored, the input, the data is stored in parallel, but we read the data in a serial manner. Similarly, this is another type of register where the data is stored in the serial manner, but we can read the data in parallel. Okay, this is called serial in parallel out. Okay, so you can store the data you can store the data in serial manner, but the data you can read in parallel. Okay, and this is your another, this is your right, rotate right. If you want to rotate the data, then okay, this is your rotate right register. This is also your shift register, because you are shifting the data. You can notice the data is shifted from left to right. So this is your base, this is your, I can say, this is your right shift register. But okay, here what is happening, the data is rotating. Okay, now focus on this. Here the data is rotating, but on the left direction. So this is called rotate left. Now all these are basically, you can notice all these are different type of register. So you can notice one thing, let me tell you, that register, that is, okay, register is n bit storage device, that is fine, there is no problem. Okay, all these, you can notice all these are actually, I can say that these are 3-bit storage device. This is a 3-bit storage device, this is a 3-bit storage device. All of them are 3-bit storage device, that is fine. Okay, so the register is a n-bit storage device, this is fine, there is no problem here. Okay, so but you can notice how the data is moving. Okay, how the data is moving, how the data is moving uh, within the register. okay, based on that we have different type of register. So you can notice a register is n bit storage device, but based on how the data is moving, okay, so you can notice, okay, you have many type of registers how based on how data is moving, okay, so you can notice based on how data is moving within the register, within, okay, or among the registers, or between the registers, okay, between, within the register or between the registers, okay. So okay, we have many type of registers, we have many different type of registers, okay. So one of them we have already seen. So you can notice this type of register we have already implemented, okay. I told you this is our objective and we have already implemented. How can you create this type of register? We have already seen, okay. Now we will see how to create this type of register, we will see how to create this type of register. So basically the implementation of all of them we will see now, okay. So now in the next lecture, first we will study something called, okay, so this parallel in parallel out register. Actually this we have already seen, so let me just quickly go through it, okay. So this is your parallel access register, means this is your parallel in parallel out register. This we have already seen, okay. So the data can be, we can put the data in parallel, we can store the data in parallel, we can read the data in parallel, okay. So this is called parallel in parallel out register, okay. Now let us see in this parallel in parallel out register, you can notice one thing. So we have already seen what is a parallel in parallel out register, so this we have already seen, okay. But here what I want to do, let us assume that, okay, in your computer organization subject you must have studied this, that there is something called system bus, okay. So let us assume this is your system bus, okay. And let us assume you are storing the data, let's assume you want to store the data in this register. So let's assume this is a 3-bit register. So this is your 3-bit register, and you, what you want to do, you want to store this data in this register. Let's assume you want to store this data here. So this is your system bus. On system bus, let us assume this data is coming, okay, 100, this data is coming on system bus, and you want to store this data in this register. So basically this, okay, this is what we want, okay. Now you can notice that after some time what will happen. So this is your register. What it means, it means that all the flip-flop have a common clock, okay. So this is your clock, okay. So all these flip-flops, they have this common clock, and now this system bus, on this system bus, the data you have, and this data you want to store on this register. Now after some time what will happen, after some time this system bus will be, okay, will be busy, okay, with some other data, okay. You can notice this is your system bus. Now this system bus will be busy with some other data, okay. But you can notice this, okay, you can notice that this clock, this is your system clock, I can say this is your system clock, okay. And you can notice this clock is applicable on all the hardware actually, okay, in your computer, okay. So within your computer you have many different hardware. For example, you have a mux, let's assume you have multiplexer, let us assume here you have register, and let us assume here you have some, okay, maybe you can have something, okay, some, maybe some counter, okay, maybe some counter you have here, okay. And maybe some other circuit you have, okay. So you can have some other circuit, maybe, okay, this is your some other register. So you can notice that in this computer you have many different hardware, and okay, and you can notice that all these, but okay, all these different hardwares we have, okay, many different type of sequencer circuits we have in this computer. But okay, what we have, the master clock is same, the system clock is same, okay. So the system clock is applicable on all the hardware that we have in the computer, okay. So this system clock is same, this system clock is same, okay. Now you can notice here this data we want to store in this register, okay. Now this system bus will be busy, will become busy, okay, with some other data after some time, okay. Maybe after 1 second what will happen, this system bus is busy with some other data, so this data will change. Now once this data is changing, but this system clock is okay, this system clock, this is constantly applicable, okay. This is constantly applicable, so this system clock is constantly applicable. Now what will happen, after some time this data will change, because the system bus is busy with some other data. So let us assume some other data is coming on the system bus now. But what will happen, when this clock will go from low to high, then this new data will be stored here, okay. Now you can notice, okay, but we don't want that, we want to store this data, this 100, okay, this data we want to store. But what will happen, after some time this system bus will become busy with some other data. Okay, and then you can notice when this some other data comes, let's assume some other data comes here, let us assume some other data comes here. Okay, now when this clock is going from low to high, then what will happen, this new data will be stored in this register and this previous data will be lost. Okay, so this data will be lost. This is not what we want. Okay, so you can notice this type of things you have studied in computer organization. Okay, this system bus, register and all these things. Okay, so you can notice this is not what we want. So what we need some type of functionality we want that. Okay, basically we want to choose when to store the data. Okay, so this is the point. Okay, we want to choose when to store the data. We want to choose, we want to control, I can say. Okay, we want to control. Okay, when to store the data, when to store the data, when to store the data. This is what we want to do. Okay, we want to control, okay, we want to control when to store the data, because you can notice this system clock. Okay, this system clock is constant. This system clock is applicable on all the hardware that you have in your computer. Okay, so this system clock is applicable on this register also, on different register also. So you cannot control the clock. Remember, you cannot control the clock for this register, you cannot control the clock. Okay, because this system clock is applicable on all the register, on all the counter, on all the hardware that you have in your computer. So this system clock we cannot control, but what we want to do, we want to control when to store the data in this register. Okay, so this is what we want to control. Okay, and to control that we need something called load signal. So what we do, okay, we want, okay, there is another. Okay, so we use, so basically we use something called load. Okay, we use something called load signal, or you can say we use something called load input. What it means, it means that whenever this load is 1, then the data should be stored. Okay, and when this load is 0, then the data should not change. So this is what we want. Okay, so you can notice basically this is what we want, that when this load is 1, okay, then this data must be stored. Okay, then data must be stored. Okay, so if you want to store the data, then you make load equal to 1. So when this load is 1, then data must be stored. Okay, and you can notice when this load is 0, then data should be unchanged. Okay, data retained, or I can say data should be unchanged. So this is what we want. Now you can notice that. Okay, so now you can notice once you have this type of, load input. Okay, then we can control when the data will be stored. Okay, let us assume here, let us assume there is some load input here. Let us assume there is some load input here. Let us assume there is some load input here. Then what will happen? Now you can notice if this system bus is busy with some other data, now also we don't have to worry. Why? Because we can make this load equal to 0. Okay, just make this load equal to 0. Now what will happen? Now this data will not be stored in this register. Okay, whenever this clock will go from low to high, this new data will not be stored in this register. So this is how we can control when the data will be stored in this register, and this is very important. So remember, we want to control when the data will be stored in the register. So for that we need something called load signal. Okay, so a new signal we want, that is something called load signal. So when load equal to 1, then data must be stored. Okay, and when load equal to 0, then data must be unchanged. Okay, so this type of functionality we want. Okay, so now how can we implement this functionality? Okay, so very simple. Let us assume you have, okay, so let us assume you have 1 bit register. Just focus on 1 bit register. Let us focus on 1 bit register. So let's assume that you have this register you have. So this is your D flip flop. Okay, this is your output and this is your clock, and you can notice that. So this is your input and this is your output. Okay, now as I told you that we need something called load signal. We want to put some load signal here. Okay, we want to control when the data should be stored in this register. This is a 1 bit register. Okay, and this is your clock. So we cannot control the clock because clock is the system clock. Okay, so we cannot control this clock is basically a, okay, I can see this is a constant, pulse. This is a constant pulse. Okay, now you can notice every time this D flip flop, this is a positive edge triggered. What it means? It means that whenever this clock will go from low to high, then this flip flop will be triggered. Okay, whenever this clock is going from low to high, then this input data will be available on the output. Okay, now you can notice that Now we need something called load, so that we can control when the input, when to store the data, when to change this output. We want to control that. Now we need something called load input. So okay, so what we are going to do, we are going to put one load signal we are going to put. Okay, so this load input, we are going to put one more input, that is load input. This we want to put, but how to put it? Okay, how to put it? So this is very simple. We can use multiplexer. Okay, because remember, we want this functionality. Just focus on this this functionality. When this load is 1, then what we want? Then we want this input to be stored. Then this q should be equal to in. Okay, and when this load is 0, then this q next, should be previous q. Okay, so this is what we want. I hope this is clear to everyone. So remember what we want. Okay, so you can notice this is okay. So when this load is 1, then we want to store the data. When this load is 1, then this data we want to store. So the q next, the next state should be in this input. Okay, and when load is 0, then what we want? We want to retain unchanged. Okay, so this q next should be q. So this is what we want. And how can we implement this? So we want to implement this, then we can use the multiplexer. So what we can do here, very simple. Okay, so I can just put one multiplexer here. So let me put one multiplexer here. So this is your multiplexer. Okay, so let me just put one multiplexer here. So let me put this multiplexer here. Okay, and here I will put this load. Okay, and you can notice this. Okay, so this is your multiplexer. This is your 2 by 1 multiplexer. Okay, so this is your 2 by 1 mux. Okay, this is your clock. Okay, so you can notice this is your D flip-flop. Okay, and this is your output. Now what we want when this load is 0. Okay, so this is what we want. When this load is 0, then what we do? Then this When this load is 0, then q next should be q. Okay, so you can notice, let us assume this is 0, this is 1. Okay, or you can say, okay, maybe this is 1, this is 0. So let's assume that this is okay, this is the multiplexer. Okay, let's assume this is the 0 and this is 1. Now you can notice that when this load is 0, then what we want? We want basically this q next must be same as q. So what we want to do, this q next should be same as q. So we can connect it here. Okay, and you can notice when this load is equal to 1, then what we want? We want q next should be equal to in. Okay, we want q next should be equal to in. So we can put this in here. Okay, because you can notice now when this load will be 1. Okay, when this load will be 1, then this in will be uh, then this in will be stored. And when this load is 0, when this load is 0, then this q, this previous output will be stored. Okay, so this is how you can control the, okay, when the data will be stored in the register. I hope this point is clear to everyone. Okay, so remember why we are putting this load. We are putting this load input. Why this load input we are putting? Okay, this load input in register, in any register, why we put this load input? Okay, this load input, why we put in any register? To control, okay, to control when the data should be stored. When the data should be stored, should be when the input data, I can say, okay, when the input data should be stored in the register. Okay, because remember, if you don't control this, then what will happen? Then whenever the system bus will be busy with some other data, then that data will be stored in the register. Okay, so this we have already seen. So basically this load input we have to control when the input data should be stored in the register. Okay, so when this load is equal to 0, then the data should be unchanged. Okay, the register data should be unchanged. Okay, and when this load is equal to 1, then we want to store this input data. Okay, so this is how, with using the multiplexer, you can control this. Okay, so you can notice this is your 1-bit parallel access register. Okay, using this multiplexer, this is your 2 by 1 multiplexer. Using this multiplexer, okay, you can notice that what you can do, you can control using this load signal. You can control when the data will be stored and when the data will be unchanged. Okay, so you can notice. So this 2 by 1 multiplexer is used to select whether to load the new value, whether you want to load the new value or you want to retain the previous value. Okay, now, so you can notice, for example, when load is equal to 0, then what will happen? because your load is equal to 0, this is your 2 by 1 multiplexer. When your load is equal to 0, then this line will be selected. Okay, then this input will be selected. So you can notice when this load is equal to 0, then this previous output will be your next output. Okay, so this I can say this present output will be the next output. So I can say when load is equal to 0, then we are retaining the old value, and when load is equal to 1, then this input data will be stored. Okay, when load is equal to 1, then basically we are loading the new value. Okay, so this is how basically we do this. Now similarly you can see 2-bit. Okay, if you want to create 2-bit parallel, okay, so this is your parallel in, you can notice the data is stored in parallel and the data is accessed, the data we can read in parallel. Okay, so you can notice this is parallel in parallel out register, and you can notice using the load, basically this is your PIPO. I can say this is your 2-bit PIPO, parallel in parallel output register. Okay, register using with load control, with load control. Okay, so using this load signal we can control when the data will be stored and when to return the previous data. Okay, basically when the input data should be stored and when the data should be unchanged, when the register data should be unchanged. So you can notice here again the same. Okay, we are doing, this is your 2 by 1 multiplexer. Okay, so we are putting this 2 by 1 multiplexer, and you can notice when this load is equal to 0, now what will happen here? Okay, you can notice here when this load will become 0. Okay, just notice here what will happen when this load is 0, then what will happen, then this line will be selected. Okay, so you can notice this will be selected, this will be selected. So when this load is 0, then this will be selected. Okay, so when this load is 0, then what is happening, when this load is 0, then what is happening, so here this will be connected, I can say. Okay, so when this load is 0, then you can notice that the previous output, okay, the present output is the next output. Okay, so you can notice the present output is the next output. But when the load is 1, okay, you can notice when the load is equal to 1, then you can notice the new data will be the new data will be stored. Okay, when the load is 1, then the new data will be stored. Okay, so similarly you can create 3-bit parallel register. Okay, PIPO register. Okay, and remember this is very important that in a register all the flip-flop they have the common clock. Okay, so notice that all the flip-flop are on the same clock cycle. Okay, so remember in a flip-flop in a register all the flip-flop they basically they are operated by the same common clock. Okay, so this is your 4-bit PIPO register using with the load signal. Okay, so remember this multiplexer, why we need this multiplexer? This multiplexer we are using because of this load signal, because okay, because we want to control when to store the data and when to, okay, retain the data. So this is what we want to control, so that is the reason. Now you can notice here, okay, when the load signal will be 0, then you can notice that we are basically the present output will be the next output. Okay, so we are retaining the data. And when the load signal will be 1, then the new data that you are applying, the new data will be stored. Okay, so this is the point. Okay, and remember, so finally I can say this is my final point. Okay, so in a register all these things that you have, in a register you have these things. Okay, what is a register? In register, first of all, let us assume you have n bit register. Let's assume you have n bit register. In this n bit register, first of all, you have n flip flops. Okay, now second, what you have, there is something called, okay, clear input. There is something called clear input. Okay, so there is something called clear input. This is clear input. This is, okay, used to clear, used to reset or clear, okay, the register content. Reset means basically making 0. Okay, reset or clear, what it means, it means making 0, making everything 0. Okay, so for example, if you want to clear your register, you have a register. In this register, let us assume this is your data. Now if you want to clear it means making it 0. Clear means making it 0. If you want to clear it, then what you can do, you can use this clear input. Okay, so this clear input we have to clear the data, and this clear input is normally, usually this clear input is active low. This is usually active low. Okay, so I can say this clear input is usually active low. This is usually active low. Active low means, what active low means, it means that when this clear is equal to 0, okay, usually this clear is I can say this clear input is active low. What it means? It means that when this is low, when this is zero, then it will make its function. Then register will be cleared. So when this clear input is zero, then register will be cleared. Okay, and when this clear input is one, then okay, register unchanged. Okay, so basically, okay, register, I can say normal operation, normal. Okay, normal operation. Oh, so register normal operation will be performed. Okay, so this is the idea. The third type of input you have, that is something called load input. Okay, that is something called load input. This we have already seen. Okay, this we have already seen that when load is equal to 1, then new data, store new data. Okay, new input data. Okay, so store. So the new data that you are applying, the new input data that you are applying, okay, is stored. So just store it. Okay, and when this load is equal to 0, then basically previous data retained. Okay, so I can say the previous data retained. So basically unchanged. Okay, don't change the data. Okay, so this is your load input. So in a register basically you have these things. If you have n bit register, then you have n flip flop. You have something called clear input. This clear input is used to clear the content of the register. Okay, and this is normally active low. What it means? It means that when this clear is equal to 0, then register will be cleared. Okay, and when this clear is equal to 1, then register will perform the normal operation. And there is something called load input. I told you why we need this load input. This load input is needed to basically to control when to, okay, store the data. This is to control. Remember this is to control. Okay, when to store the data, when to store or retain, when to store or retain, uh, I can say, okay, when to store or retain data. If you want to store new data or you want to retain the previous data, so for that we need this control input. Okay, you can also have some more input. For example, you can have something called, okay, this preset. You can have something called preset. If you want to preset your okay, preset means basically making one. Okay, let us assume this is your register. In this register, let us assume right now this is your data, let's assume, and you want to, okay, you want to perform some operation on this register. And before you perform that operation, let us assume that you want to, okay, make all these one. Okay, so then you can use this preset input. Okay, so basically preset means making everything one. Okay, so this preset means basically making everything one. I can say this simply means making everything one. Okay, so preset means preset. So what will happen? So all these will become, so basically this will become, okay, so this preset input also you can have. Okay, for example, you can take this. Okay, this is your, what is this? This is your 4-bit parallel in parallel out register. This is your 4-bit parallel in parallel out register. With, in this you can notice, with, in this you have load input. Okay, in this you have reset input. Reset means clear. In this you have reset input, and in this you have preset input. Okay, so in this you have reset input, preset input, all these you have. Okay, so in this register you can notice, so we have load input, and we also have preset input, and we also have a reset input. Okay, you can notice that this preset is also active low. Okay, so this preset, this is your preset, this preset is also active low. You can notice that this reset is also active low. You can notice this is active low. Okay, so this is a symbol for active low actually. Okay, so let me tell you that this preset is also, this preset is also usually active low. This is also usually active low. Okay, and the symbol for active low you already know, the symbol for active low. Okay, what is that? Symbol for active low is something like this. Okay, this is the symbol for active low. You can notice. Okay, so this reset means clear. So you can notice this is also active low. What it means? It means that when reset is equal to 0, then all these flip flop, all these, okay, all these outputs will become 0 0 0 0. Similarly, when this preset is equal to 0, when this preset is equal to 0, then all these outputs will become 1 1 1 1. Okay, so I can say that, okay, when this preset is equal to 0, when you do, okay, when this preset is equal to 0, then what will happen? Then this will become 1, then this will become 1, then this will become 1, and then this will become 1. Similarly, you can notice that when this reset is 0, when this reset is 0, then this will become 0, this will become 0, this will become 0, this will become 0. Okay, so this is the application of This is the use of preset, comma, clear, comma, load. Okay, so you can notice in a register normally you have clear input also, you have a load input also, and you have a preset input also. All these inputs you have in a register. Okay. Okay, so this is the point. In the next lecture we will study some other type of registers, because the one type of register we have seen, and that is parallel input, parallel output. Okay, we are storing the data in parallel, we are reading the data in parallel. Okay, so parallel in, parallel output. Okay, so this type of register we have already seen. We have also seen different type of inputs in a register. Whatever register you have, in that register you can have some extra inputs. For example, you can have load input, you can have clear input, you can have preset input. So these extra inputs you can have. These extra inputs will basically give you some more functionality. This load input will give you basically a facility to control when the data should be stored or the data should be retained. Okay, similarly clear input and preset input. So all these concepts we have seen, and now in the next lecture we are going to see some different type of registers like serial in, serial output. Okay, and all the other different type of registers that we have already talked about. Okay, thank you everyone.